All right, so a couple of kind of definitions here. So the line tangent to a graph. So if we're given that point T where we're going to be tangent to, and the close points P sub n on the graph of a smooth continuous function, the tangent line at that point T is the limiting position of the secant lines through point T and increasingly close points P sub n. So like we said, if we go back here, as we get closer and closer and closer, that limit as P goes to n, that's going to give us that slope of the tangent line as well, which is the solid blue line. Okay. And so the general rule for tangent lines is tangent lines are going to be to a smooth linear graph. Do not cut through the graph at the point of the tangency. They just get, lie completely on one side of it. They just kind of nick that point where it is, but they don't cut through it, except for an inflection point. And that's going to be the only place where it actually cuts through the graph. Otherwise, it's going to be either on the top side or the bottom side of a graph. So looking here at this one, these are two different ways looking at tangent lines. So this one, we can see the tangent line comes right up to that point, but it never crosses and cuts through the graph. It's tangent to it, and it's below the curve. So it's actually below that curve. It's not above the curve or through the curve. It's below the curve. And this one, it's all above the curve. Now, granted, this one, it doesn't cut the curve anywhere else. This one does cut the curve, but we're only worried about where it's cutting the curve here. It's not cutting it. It's right above the graph there. It's not actually, through the graph at any point. It's right above it, near that point of tangency. Okay. Now, this is the exception with the inflection point, and so they're kind of showing some wild possibilities for writing tangents. And S, that's not how you're going to write a tangent. And the R here. Now, if we go and make this bigger screen, maybe it help us a little bit, not much, but we can see that the R, it's cutting through the line here, then it's going through their point P, and then it's cutting above the curve here and going on. And that's not what we want. What we want is on an inflection point, the T is going to be above this curve on this side, and it's going to be below the curve on this side, and it's just going to go right through that point. So it's going to kind of go through the inflection point and get as close to being touching nothing but that point as possible. Now, when you're drawing this by hand, that's going to be a little more hard, or even, when I'm going to show you a little bit later, drawing it by computer, it's not so easy. But that's kind of the thing. The R and the S are not tangent, and they're kind of showing you extremes. They could have gone this way as well, and it's not a tangent. We have to kind of come through and then just go right through that tangency point and go under this side of the curve and over this side of the curve. Okay. All right, so we have some more calculations here. So we have a rate of change of a function. Now, at that point on a smooth continuous function f, the rate of change of the function is given by the slope of the line tangent to the graph. So that line tangent to the graph, we find that slope, that's going to give us the rate of change. Okay. And now, and of course, unless the tangent line is vertical, then, then we don't have a slope there. And so then our rate of change is now denoted as f prime of x. So, have a rock. Now we have this is going to be called f prime of x. Now the percent rate of change of a function, again, for a smooth continuous function f, if the rate of change is that f prime of x that we just found there at x0, and it exists for a certain input value x0 where the f of x0 is not equal to 0 because we can't have that equal to 0, then basically our percentage rate of change is that rate of change of a point, that f prime of x, whatever we found up here, divided by the value of the function at that point. So, if it was that point, this is say 4, then that's 4 and maybe that's 200 or something like that. We're going to use the value of the function at that point times 100%. And here the unit of measure of percentage rate of change is the percent per single unit of input. So whatever it is, years, hours, whatever, we have to just kind of base it on that. All right, so let's go on, and I think we're going to start with problems next.